In this video we're going to talk about wind sensitive structures in RCB. So we're going to have a review of the wind code, so AS/NZS 1170.2. So all of the input parameters that are needed to calculate wind force. So not just the section 6 advanced ones, but all of the other ones that are needed to calculate the drag forces. We're going to talk about wind sensitive structures, what it is, and how to determine if our structure is wind sensitive. And we're going to talk about the along wind and crosswind response. So talk a bit about fluid dynamics, what are the effects of generating these forces, and then we're going to talk about how we combine the along wind and crosswind forces in the software. And we'll also talk about the Appendix G acceleration of the top floor that is considered by RCB. So we're not going to use the RCB software. We assume that the user has watched the input lateral loading videos, so they're aware of how to input lateral loading in the software. This will focus more on the theory, but we will, however, use the same example that we have in the previous videos. So wind is random in nature. Wind loading is random in nature and described using statistics. So it's turbulent and varies both in space and time. What we mean by turbulent, if we look at this particular picture, we have the wind going over a rough boundary layer, the surface of the earth. So it's flowing over houses, terrain, trees, whatever. And as it flows over, basically the flow shears. It's not nice, smooth and laminar. So imagine the flow going over an aircraft wing. Nice and smooth, not like that. It's turbulent. Turbulent, it's more like, for example, a wave breaking in the surf. So the flow shears, rolls over itself, generates these eddies, what are called eddies, of varying size and shape, which basically hit our structure randomly and apply force randomly onto our structure. So we have to describe this randomness using statistics. Wind loading is basically split into three orthogonal directions. So let's imagine the wind is blowing in the x direction, so the along wind is in the x. We have a force applied in that direction as well. We also have a force applied in this sort of perpendicular direction in the v, so this is referred to as in the crosswind direction. And there's also an additional application of force vertically in the w as well. Now, the wind code only considers wind loading applied in the along wind and crosswind direction. This vertical component of the loading is not considered in the wind code, AS/NZS 1170.2. How wind speed and hence wind force is determined is by an instrument called an anemometer. So here we see two pictures, the one on the left being this older analog Dines pressure tube anemometer. So in Australia, all wind speed was determined using this Dines pressure tube until about the mid-90s. After the mid-90s, it was replaced with this digital anemometer called an automatic weather station. So what these instruments produce is they produce an anemograph. So they give us basically time on the horizontal axis, and on the vertical axis we have wind speed and wind direction. So looking at wind speed, we see that there's quite a bit of fluctuation over these 600 seconds of the maximum and minimum wind speeds. So we see a minimum of 0.26, maximum of 8.5 meters a second. So as structural engineers, we're interested in this peak value, this peak gust wind speed. What we mean by gust, it's not a constant wind speed, it's just basically a peak gust at an instant in time. So this is basically what is going to govern this ultimate design. It will generate the largest drag force on our structure. The other thing that we're also interested in is the mean wind speed as well. So it's this constant mean wind speed that's going to be generating all of our crosswind forces. So we'll talk about this in more detail in later slides. And from the bottom picture here, we see that the direction fluctuates as well. So not only the speed, but the direction. And from this, we get a mean direction, in this case, a westerly wind. So in summary, what our wind code is doing is it's converting all of the available anemometer data in Australia from the last 50 to 100 years into regional wind speeds that we then use for design. As there is relatively little wind data available in Australia, Australia hasn't been around that long, we only have 50 to 100 years worth of data, we have to extrapolate this data to calculate our ultimate events, so our 200, 500, 1,000 year events. So in essence, what the code is doing, it's converting bluff body fluid mechanics and any related dynamic effects into relatively simple factors and equations. So anything that's going to be influencing our wind speed is accounted for. So the terrain, the shielding, the direction, the topography. The wind speed is then multiplied by these factors to get an equivalent static wind pressure. And so that's for the along wind and crosswind directions. So it's important to note that our code only deals with ultimate events. The code does not deal with serviceability wind events. So, for example, service wind speeds affecting the usability of our structure, the comfort levels of particular sections of our building. The wind code does not consider that. Only will our structure be okay, will it stand under that particular wind load. So it's based on peak gust wind speeds, so that highest value from the anemograph, terrain category 2, and wind speed at z equals 10 meters height. So this basically is where the anemometers are located, and then everything is just sort of normalized to these values. And the code considers along wind and crosswind dynamic forces. So these dynamic effects are converted into equivalent static forces, which we then apply to our structure. We're going to our example that we've looked at in previous slides. We have a typical floor plan, more or less square in shape, approximately 22 meters in the X and Y dimensions, and 49 meters high. So for this particular example, we'll assume that the building is located in Sydney's lower North Shore. Now, in reality, it's not located here, but for this example, we'll assume that it is. So the first thing that we need to do is to check, are we within the scope of the code? Can we use the code at all? So the building is less than 200 meters, good. Roof span less than 100, good. And we are not one of these structures that the code does not consider. Therefore, we're okay, and we can use the wind code to calculate equivalent static wind forces for our building. So the first set of things that we need to input are used to determine our regional wind speed. So our region is A2 Sydney. We are a residential building, so importance level 2, which gives us a recurrence interval of 500 years. So we put in the wind region and the recurrence interval, and the program automatically calculates the regional wind speed of 45 meters a second. So all done automatically. Now, where do these regional wind speeds come from? Well, in short, the answer is statistics. So what we have here is the yearly peak data for this particular location that is normalized and ranked. So we have basically wind speeds, peak wind speeds from various years. The probability is calculated and plotted. And then a line of best fit is plotted to determine mode and dispersion. And then from that, the recurrence interval wind speeds are calculated. So we see that these wind speeds are based on the amount of data available. So we have quite a bit of data bunched up here, but there's also a subjective element to it as well. So do we or do we not consider these outliers? If we were to take out this particular point, for example, that would affect our values, and hence our wind speeds, and hence the force that is generated on the structure itself. So yes, in summary, determined using statistics, but influenced by the amount of data available, but there's also a subjective element to it. So do I include this value? Does this value make sense? Was the machine working correctly at that particular time? The next thing that we input is the wind direction multiplier. So not considered automatically by the software. We have to go to table 3.2, see that for the along wind positive x direction, we are a westerly wind, which gives us a directional multiplier of 1. So that's done manually by the user. The terrain category, so we get a map, we draw our averaging distance, and we can see that basically everything in every direction is terrain category 3, so suburban housing. We have some small segments that are terrain category 1, but for the purposes of this example, we'll ignore them. What the program does not consider is changes in terrain category. So if we were to follow clause 4.2.3 exactly, and if we were to have changes in terrain category present, we would have to basically calculate an average. So based on the averaging distance, we calculate the distances and terrain categories and get an average value. We then repeat that calculation per floor, or basically height location that we're going to be calculating forces at, and then we repeat that for the various directions as well. So this is not done by the program, so we have to use the worst case one. We can only input one terrain category. So we just put in the terrain category in the software, and the program automatically calculates MZCAT for us. Next thing that we input is the shielding multiplier. So suburban housing, to clause 4.3, this tells us that shielding is 0.85. However, the maximum shielding height, the maximum buildings around us are 10 meters tall. Our building is 50 meters. So basically, we're just going to be conservative and assume that these smaller buildings will not apply shielding to our structure. So RCB does not consider shielding only on, for example, the lower 10 meters of our building, so we'll just assume that none of it is shielded and take MS equal to 1, which we put in. Next, we put in the topographic multiplier. So for this particular example, I went through and calculated this by hand. Here I have a topography plot. I see that next to our site there's a drop-off, there's a cliff. So in Australia we have no lee zones, so this the topographic multiplier is equal to the hill multiplier. And not going through the calculations in detail, but basically following the relevant table and the equation for a particular height, we see we have some some topographic multiplier. We see the topographic multiplier changes over height, but in this case I just put the worst case one at 10 meters. So RCB does not consider topographic multiplier changing over height of the building. We're only allowed to input one value, so I just input the worst case one of 1.05 for this particular direction. And if following the code to the letter, I would have to calculate this per wind direction. This is just for one wind direction. I would have to repeat this for all other wind directions as well. Or I could just take it as one and be done with it. So using these multipliers, the program automatically calculates a site wind speed. So we have the VR value that is determined from the recurrence interval, and then we have the various factors that we've input, and the program automatically determines a site wind speed for us to clause 2.2. Then what the program assumes is that the site wind speed is equal to the design wind speed. What is the design wind speed? How it differs from the site wind speed as defined in the code is that the design wind speed is the worst case site wind speed in a plus minus 45 degree radius from the face of the building being considered. So for example, if the wind is coming in hitting this right side face, we would have to calculate wind speeds in a plus minus 45 degree segment and get the worst case site wind speed. That will then be our design wind speed. RCB does not do this. We assume that whatever site wind speed calculated by the software is the worst case one in a plus minus 45 degree radius, so that is what we use as our design wind speed. So it's, again, if there's changes, if there's going to be some worst case value, be it either by shielding or terrain in that plus minus 45 degree segment, that is basically the user has to consider that by themselves manually. The program will not consider it. So the program, in summary, considers site wind speed to be equal to the design wind speed. So the forces due to the wind. The code is converting this design wind speed into an equivalent static force. So the drag forces due to the structure's shape are accounted for using the C fig factor, And the dynamic forces, which are also converted to equivalent static forces, are the dynamic response of the structure. They're accounted for using the C dynamic factor. So before we look at these values in detail, we'll just have a quick look at some basic bluff body aerodynamics and how it relates to the wind code and how it relates to the structure. So looking at this particular shape in plan, so more or less the shape of our building, a square cross section, we see the wind coming in the positive x direction. These lines represent lines of flow. We see that when it hits the building at the center and the flow stagnates, so that is the point where we have the highest basically equivalent static pressure. And the other flow basically goes around the side of our building. It separates at the corners, so that's where we have these peak values on the side walls. The flow shears, we get some turbulence along the sides, and then we have a turbulent wake along the building. So hence we see sort of peak values on the side of the building and more or less constant pressure on the back of our building as well. So in terms of what RCB is doing, RCB in plan is only considering the windward and the leeward walls, regardless of shape, be it rectangular, square shape, whatever is modeled. Side walls aren't considered. The reason being is that when we're calculating, for example, bending moment at the center of the building, the bending moments generated by the side walls will cancel each other out and will have no effect. So we only look at windward and leeward. Again, looking at the same problem in elevation, same thing, flow stagnates. We have some flow hitting the building, reversing backwards, flow going over the top, shearing, generating some wake, and then we have basically turbulent wake at the back of the building. So the pressure distribution as generated, as calculated to the wind code, as we will see in the software, has a parabolic distribution on the windward face. So parabolic distribution, this is caused by the effects of surface roughness. So closer to the surface, closer to the ground, the wind flow is slowed, so the wind force is lower. And the further away we get from the ground, the higher the wind speed, the higher the force. The leeward wall, the constant pressure, basically this is governed by the wind speed at the top of the building. This generates this turbulent wake, which generates sort of a constant suction on the back of our building. Along the roof we have some varying distribution of the wind force, but RCB assumes that this will be more or less constant. Hence any moments that it generates at the base of our building will cancel each other out. So again, in elevation we don't look at the roof, we're only looking at windward and leeward walls. So this is all we've been talking about so far, has just been external pressure. So what about the internal pressure? So here we see how the internal pressure coefficients are calculated. However, these internal pressures are constant over the entire internal surface. So any forces that they generate will be constant and will cancel each other out. So RCB does not consider internal pressures because they won't have an effect on our final results. So with that in mind, we calculate our aerodynamic shape factor, C fig, in the along wind direction. So these that will then be used to calculate our forces due to drag. So here we see the equation. We have our pressure coefficients as calculated to the relevant tables for our windward and leeward walls. The local pressure for cladding is 1 because we're not designing cladding. Permeability reduction factor is 1 because walls aren't permeable. Area reduction factor also 1 because this is only for roofs and sidewalls. It's not applicable to windward and leeward walls. And the combination factor of 0.9 lets us slightly reduce the value because we have combined wind forces acting on our windward and leeward wall. So not done automatically by the software. The C fig value, the aerodynamic shape factors, must be calculated manually by the user and input. So in this case, for the windward wall, 0.8 drops down to 0.72, and leeward 0.5 goes down to minus 0.45. So it should be noted, we can put in positive or negative values for leeward. The program is just taking absolute value, so it doesn't matter if this is plus or minus. So that is for the along wind direction, the aerodynamic shape factor C fig. Now, what about C dynamic? So the first question that we have to ask ourselves is the structure wind sensitive? So in the previous frequency video, we saw how to generate a frequency report, how to get the frequency values, and we use that frequency report to determine if our structure is sensitive to dynamic wind excitation. So here we see that the first natural frequency of 0.29 Hz is less than 1 Hz. Hence, as defined in section 6, our structure is less than 1 Hz and is wind sensitive. Therefore, we have to calculate along wind and crosswind responses to section 6.2 and 6.3. We have to calculate both of them because both along wind and crosswind forces will be present. It's not just one will be there, the other one won't be. They will both be there and both must be considered. So looking at this report, why I chose this 0.29 value as opposed to 0.246, this had a higher mass participation in the X, meaning that sort of this is the first dominant one in one direction in the X. The other value of interest is the second natural frequency in the other direction. So here I've taken 0.363, well, I've used 0.4, which I'll mention why in just a moment, for the Y. So we need a natural frequency in the X and one in the Y. So NX equal to N1 0.29, N2 equal to NY 0.363 or 0.4. So before we do the section 6 calculations, we have to see, are we within the scope of section 6? So N1 greater than 0.2 Hz, good. However, N1 and N2 are both less than 0.4. So strictly speaking, for these values, we can't use the code. However, what I've assumed is that the structure's in the preliminary stage. I haven't put in, I've just got 32 MPa concrete in my walls, so I haven't put in my material properties. Slab thicknesses aren't finalized, wall layouts might not necessarily be finalized as well. So I'm assuming the structure will be stiffer. I'll be able to get that these values will probably be a bit higher in reality. So I assume I will be in the scope of the code. So just for this exercise, I'll take N2 equal to 0.4 Hz. So with these natural frequencies determined, we've determined our structure is wind sensitive. So we now go ahead and let the program automatically calculate the along wind response and crosswind response for us. So along wind response, dynamic response factor C dyne. So this is calculated to 6.2, and it's calculating the along wind dynamic response caused by turbulence buffeting. So what we mean by turbulence buffeting, if we look at this little screenshot of the anemia graph, we see a fluctuating wind speed. We also see this turbulent flow generating random eddies of random size, hitting our building randomly. So basically, we don't have a constant load applied to our building. The building is being buffeted randomly with a force of varying magnitude on the windward face in the along wind direction. So this is basically, this is what is being considered by the C dynamic factor. The program automatically does the equation 6.2 calculations for us. We'll just have a quick look at this equation and just to understand what it's doing. So all of the calculations that were talked about previously were referring to a peak gust wind speed, so that highest peak value in the anemia graph. However, as we're now looking at dynamic forces, we need basically the mean wind speed. A dynamic response is generated by a constant wind speed, basically the constant wind speed. So what we need to do is we need to convert this peak gust wind speed to a mean wind speed. So in section 6 you'll see a lot of this 1 divided by 1 plus 2 GVIH. This is converting a peak gust wind speed to a mean wind speed. The turbulence intensity at a particular height is automatically calculated by the program. The only thing that we need is the natural frequency which we determined already from the report, and the ratio of critical damping, ratio of structural damping to critical. So in this case 0.03 for an RC structure as defined in clause 6.2.2. So within the program we switch on, we know we're wind sensitive, so we have to switch on the along wind clause 6.1. Crosswind is automatically switched on. It will be there in reality. And this C dynamic grays out, meaning the program will calculate it for us. So we put in our damping ratio, structural damping to ratio of structural damping to critical damping, and we put in some natural frequency. So for this particular case, we'll assume that NA, so the subscript A being the natural frequency in the along wind direction, is equal to the first natural frequency. I'll talk about which one is which in just a moment. So the only thing we need to input for the calculation of C dyne is switch this on and put in the damping ratio and the natural frequency in the along wind direction. With that input, the program automatically calculates the design wind pressure for us based on the equation to clause 2.4.1 for the along wind windward and leeward walls. So the density of air of 1.2 kilograms per meter cubed is a constant value in RCB. So just one thing of interest is that this 1.2 kilograms per meter cubed density is conservative for tropical regions where the density is lower, but unconservative for colder regions where the density is a bit higher. So next we'll talk about the dynamic forces due to wind, the forces that are being considered in section 6 of the code. So here we have this square-shaped structure in plan. We have the wind direction in the positive x. So in the along wind direction, the direction of the response will be in the direction of the wind, in the along wind direction, and as we mentioned previously, the event that we are considering is turbulence buffeting. So in the along wind direction. In the crosswind direction, we consider turbulence buffeting and wake excitation. So what we mean by crosswind is wind in one direction, but the structure's response is perpendicular to the direction of the wind flow. So as we said in the very first slide, wind not only applies load in the direction of the flow, but also perpendicular to it. So this turbulence buffeting caused by the shearing of the flow, these eddies hitting our building, not only is that happening in the direction of the wind, but also it's hitting our building side on as well. So we have turbulence buffeting in the crosswind direction, but we also have wake excitation. So what we mean by wake excitation, we'll just have a look at these screenshots from some computational fluids software. So wake excitation is caused by vortex shedding, and this wake excitation is what is generating predominantly this crosswind force. So this is highly dependent on the shape of the structure. So here we see our square-shaped structure. It will be different for a for a rectangular shape. And this is what is considered in clause 6.3. So here we have the wind in the X, and basically as the flow goes around the building, we have some vortex forming, which will then basically shear and break off. As it breaks off, it loads the structure in one direction. As that has broken off from one direction, it is basically the same thing is happening. This vortex is building up on the other side of the building, which then sheds off. As it sheds off, it applies load, and basically then the process repeats on the other side. So we have this oscillating force that is going plus minus, this dynamic oscillating force plus minus in the y direction. So essentially the crosswind section of the code is converting this dynamic action into an equivalent static force. So what is needed in RCB to calculate these values are basically the natural frequencies in the along wind and crosswind directions. So they're not the first and second natural frequencies. They're not N1 and N2. They're referred to as NA, the subscript A meaning along wind, and C, the subscript C meaning crosswind. How we determine which one is which one to use? Well, we'll go through that now on our example. So we saw from the previous slides, we have our first natural frequency of 0.29 Hertz, which is in the X, and the second natural frequency of 0.4 Hertz, which is in the Y. So for the case that we have a long wind in the X direction and crosswind will be in the perpendicular Y, We know that basically the first natural frequency was in the x direction, hence our along wind is in the x direction, so our NA value will be 0.29 Hertz. For the crosswind direction, crosswind is in the y, our second natural frequency was in the y, hence our NC value is equal to 0.4. So for this direction, we have NA equal to 0.29, NC equal to 0.4. When the wind direction then changes to the y, basically these values flip around. NA becomes N2 of 0.4 Hertz, NC becomes N1 of 0.29 Hertz. So basically that's all there is to it. From the report we get the first and second natural frequencies, or the ones in the x and the y direction, and then we determine which one to use based on the direction of the wind itself. So those are the two inputs that we need for the along wind and crosswind. What the program is doing internally is that for some but it's calculating the crosswind force spectrum coefficient to the wind code. So these very complex computational fluid, this very complex fluid dynamics that is occurring when the wind is loading our structure, AS1170 is trying to simplify that into some basically some factors that we can use in our design. So based on a range of shapes, so shapes with a specific height to breadth to depth, it calculates some reduced velocity. We calculate some reduced velocity, which we then use these tables to get a crosswind force spectrum coefficient for. So if our structure doesn't fall within these standard shapes, the program linearly interpolates. For our case, the height to breadth to depth ratio was 2.3 to 1 to 1. This falls outside of the standard shapes as defined in clause 6.3.2.3. So the program will use the one that is closest to it. So the basically figure 6.2 for a height to breadth to depth ratio of 3 to 1 to 1. So this is all done automatically within the software. The software will read the height of our structure, get the breadth and the depth based on what we've modeled, the average breadth and depth of the entire structure, and then determine which table to use. So all done automatically, and basically in RCB, and what the wind code is doing is basically converting this complex fluid dynamics into relatively simple tables for some standard shapes. The only other input other than the along wind, crosswind natural frequencies that are needed is basically this mode shape power exponent. So this is simply one for our case, building with a central core and moment resisting frame. So using these values, we calculate a C fix C dyne value, which we then put into this equivalent crosswind force at height Z. So this is all done automatically within the program. So despite having very few inputs for along wind and crosswind force, the program fully considers all of the requirements of section 6 and is automatically determining the size of the structure that we've modeled. So all fully considered within RCB. So pressing OK on that window, and the program converts this into some equivalent static force for us. So this along wind drag force, along wind turbulence buffeting, crosswind, wake excitation and turbulence buffeting is all converted into some forces. So here we see along wind in the positive x, crosswind in the positive y. The program generates forces in the x and y for us. So the x direction we have a more parabolic profile, but for the y, because this is a dynamic response, we see we have very high values at the top which sort of drop off to some very low values at the bottom. Now be aware, if the building is taller, crosswind forces may be greater than the along wind force. Again, this is also dependent on the shape of the building, so don't be alarmed if you see some larger crosswind forces. That's what it is, and the program is calculating it as per the wind code. So this is just the one direction. Then we would repeat it for the negative direction and all other combinations. Now, which combinations should we use? Which combinations are needed? Well, that's all dependent on how we combine our along wind and crosswind forces. whether we choose to be conservative or whether we choose to be more realistic. So this is determined, this is covered in the wind code in clause 6.4. So the intention of this clause, what it tells us, if you refer to the commentary of the wind code, is that peak, alongwind and crosswind forces statistically will not occur at the same time. So as these papers have shown, it is conservative to apply peak, alongwind and crosswind forces simultaneously. So the intention of this particular clause is that it lets us reduce the values of the, basically it specifically relates to peak dynamic action effect. So for example, the bending moment in a column, it lets you reduce these values based on the assumption that peak, alongwind and crosswind will not occur at the same time. So what we do in the software, we assume that, for example, that bending moment in the column due to the wind is directly related to the wind force. So we apply our reductions to the to the wind force itself, not to the force in the column that is generated, for example. Now, what is done within the software is a little bit different to this particular equation. So when putting numbers into this particular equation, the results don't exactly make sense. This total force is actually sort of the same or greater than the peak forces, which doesn't necessarily make sense, which goes against the intentions of this particular code as defined in the commentary. So what we do in RCB is a little bit different. And I'll explain what we do and our assumptions in the next slide. So we'll talk about this particular slide in a bit of detail, and this is also explained in the manual. These screenshots are from the manual as well. What we're looking at here is, again, our building in plan. We're looking at the positive wind, the wind is positive in the X along, so positive X alongwind direction hitting our building. Then we have negative crosswind and positive crosswind. So from this wind force, we have basically, from this wind, we have force generated in the alongwind direction, which is shown on this bottom, on this horizontal axis, and crosswind on the vertical axis. So in all of these figures, the subscript X refers to in the X direction, A refers to alongwind, C refers to crosswind. Other subscripts that we will be referring to, P refers to peak, M refers to mean. So, if we were to be conservative, if we were not to combine, if we were to combine peak, alongwind and crosswind forces, if we didn't want to use 6.4, clause 6.4 at all, we would have this switched off. So this is in the orange. So with this switched off, we see that the wind direction to apply the load to, these drop-down boxes, the directions, both of them will always be visible. So there's a mistake in the screenshot here, that should be in the +Y. But we see that with this switched off, the program is always calculating the worst case peak, alongwind and crosswind and combining them for each case. So we have peak in the X alongwind, peak in the Y crosswind positive, and then we have peak X along minus Y peak cross. So if we're not considering clause 6.4, we would only have two primary cases for this particular direction. So this is just X in the alongwind positive. We would then have negative X alongwind, negative Y, alongwind, positive Y. So we would have three more tables such as this. So these two primary cases for the peak values will become a total. So as we can see, just from the magnitude of these these forces, these orange values compared to these reduced blue ones, they're already bigger. So we're seeing we're seeing just how unconservative we are by not considering clause 6.4. Now, How we consider clause 6.4 and how we model it is that we have to basically switch on this checkbox here. So when we switch this on, we have an option that becomes available, combination of along and cross. So when this becomes available, we have a slider that becomes also enabled, and based on the location of the slider, we apply various combinations of along wind and crosswind. So I'll explain what each of the three positions means in relation to the force that is calculated. So the simplest one to understand is when the slider is all the way to the very left. So we have wind in the x direction, we have a peak value. So when we have wind along wind x peak, the crosswind value is grayed out. Why this is grayed out? If we refer to remember the previous anemia graph from one of the earlier slides, we had a peak gust wind speed and that was just occurring at an instant in time. So when we have a peak gust wind speed, we don't have any crosswind forces. So the crosswind force is generated by a constant mean wind speed. So if we have a peak value, we can assume that there'll be no crosswind forces present. So that is why when we have this along wind peak value, which is the maximum peak value, we have 0 crosswind force. Next, we'll go to the other extreme. We'll pull the slider all the way to the very right. When that is pulled all the way to the right, we have a peak crosswind in the y. As we mentioned previously, for a crosswind force to be generated, there has to be an along wind force, and that along wind force has to be a mean along wind force. So we see when the slider is all the way to the right, we have wind in the x direction along wind mean, then we have wind in the y crosswind peak. How we calculate the mean along wind value, going back one slide, we use this equation. So we have the peak value divided by this factor at the bottom. So with the peak x value, with the mean along wind x value, we have a peak crosswind value as well. And straight away we can see when they're combined, it's already less than this orange peak value of both. So the force is already reduced. And finally, there's one more additional option when the slider is in the middle. So here it is just some value that is somewhere between peak for both. So what happens when the slider is in the middle? Both options become available. We just have x along, y cross. And what is done internally within the software is we have the peak values for along wind, peak values for cross, and we draw an ellipse. We know what the mean wind speed is in the along wind, and then we also know what the peak is when we combine both of them. So what we do is we have the ellipse, we draw a line, and we get this intersection point. So this is this intermediate point. So this is just for this one quadrant. We would then repeat it for the negative values, and we would then have to repeat it this whole table another 3 times. So where we had 5 primary wind cases plus an additional 15, we have 20. So we see that by being accurate, by being less conservative, we have to have many more primary cases and many more wind combinations. But if we were just to use these peak values, being more conservative with the peak values, we would only have to have 8. So going to the next slide, this is what the orange peak wind cases look like. So considering all directions, we have 8 total. These reduced ones, the blue ones, these are the ones that we saw. Then we have an additional one for the an additional 3 sets for the other along wind directions. Now, don't be alarmed, you don't have to type this in manually. If you go to the manual, to the wind section, where you see these figures, we have download links for Excel files for these tables, which you can then import by pressing the import button. So how we combine these, for the peak values, the orange ones, we have 8 values times 2 sets of combinations, so we have 16 combinations total if we were just to use peak for wind, which we would then design the envelope for. If we were reducing the values, we would have the 20 primary cases times 2 sets of combinations, so we would have 40 combinations for wind if we're reducing them to clause 6.4. Again, all has to be done via envelope. So all of these combinations also available for download via the manual, so just copy paste that link and then in the load combinations window hit import, and that will import it automatically. So those are the equivalent static wind forces that the program calculates, and that is all done automatically. So for every wind direction, be it 8 or 20, if our structure is wind sensitive, we just have to modify the directions and the program calculates an equivalent static force for us. Every time we do that, every time we hit the OK button, the program is basically automatically calculating the wind acceleration to Appendix G for us as well. So because it is using service wind speeds in these calculations automatically, it is using this lower critical damping ratio, which it tells us here. So how we access this acceleration is we calculate the value, we hit OK, and then we press report for that load combination. So here is a sample of the report. We have this the simplified acceleration calculations calculated for recurrence interval wind speeds for service, so going from 1 year recurrence interval to 25. And then we have a long wind and crosswind acceleration calculated in meters per second squared or milli-Gs. So all automatically done by RCB. And finally, what we didn't look at in detail, but just letting you know the program can do it, is, for example, if our structure didn't fall within the scope of AS 1170.2, and we had to get a wind tunnel test done by a wind engineer, is that we can input the results of that wind tunnel test into our structural model. So for the selected load case, we hit import. We then choose to open an Excel file, specify the rows and columns where the relevant data is located, and then import that into our model. So all fully considered, all done within the software. And finally, here are some references about the things I talked about for further reading. So in summary, the wind code AS/NZS 1170.2 converts sort of these drag forces and these dynamic forces due to wind into equivalent static forces. This is all fully considered by RCB, both the long wind and crosswind directions. All we need to do is determine if our structure is wind sensitive and then just get the long wind and crosswind natural frequencies as needed.